Good morning. Today we are going to be talking about titrations part 2. So today we're going to talk about, last class we just talked about strong acid, strong base, nice simple titrations. Today we're going to jump into weak acid, strong base, and weak base, strong acid. These are going to be a little more complicated since now we're bringing in some salts, conjugate acids, conjugate bases, all of that fun stuff that goes on. So let's kind of dive in and start talking about it. So the reaction of a strong base with a weak acid is assumed to go to completion. Before the equivalence point, the concentration of the weak acid remaining and the conjugate base are determined. So we have to use that if we're before the equivalence point. At halfway to the equivalence point, pH is equal to pKa. So I do want to talk about pKa really quickly. pKa is basically a way that we measure the strength of acids and or bases. So pKa would be for acids and pKb would be for bases. To solve for the pKa, you just take the negative log of your Ka value, your dissociation constant. So pKa is equal to the negative log of your Ka value. And for acids, it's again just used to determine the strength of acids. So the smaller the pKa, the stronger the acid. Okay. At the equivalence point, a basic salt is present. So if we have the same amount of hydrogen and hydroxide, we will have a basic salt and the pH will be greater than 7 because we have that basic salt present. After the equivalence point, then the strong base is going to be our dominant species, and we can actually just do a really simple pH calculation when our strong base is there. The pH is going to be above 7 because, guys, we have that strong base. And so it's going to have those extra hydroxide ions. Or at the equivalence point, we'll have that because we have the, oh my goodness, totally blanking right now. The acidic base, the basic salt. Sorry, wow. The basic salt at the equivalence point. Okay, so we're going to I'm going to go to a different picture of this titration curve to talk about the different points of it. But this is the titration curve of 50 milliliters of acetic acid, which acetic is a weak acid, with 0.1 molar sodium hydroxide. So sodium hydroxide is a strong base. So let's kind of talk about the different parts on this graph and also what our pH would be and how it would be affected. So this is the same graph, but I have marked it up with some things that I want to talk about with you guys. So at the beginning of our graph, so down here, right here, we only have our weak acid there. So that's the only place we have our weak acid only. So we would use our Ka then to calculate the pH, just do a normal weak acid calculation using the Rice table, all of that fun stuff. If we move along I don't know why I can't talk, our titration curve, if we're like here-ish or so, our weak acid is going to be greater than our strong base. However, we need to do stoichiometry to figure out how much of our weak acid has been consumed. And after that we do that, then we'll just do a normal weak acid pH calculation, again, using our Ka value. And then this right here, this would be halfway to our equivalence point. So this means half of our acid has been consumed in our reaction at this point. So the concentration of our acid, of our weak acid, is going to be equal to our acid after it's lost that hydrogen. So we're halfway to the equivalence point. Our weak acid is still going to be a little higher than our strong base, and our pH will be equal to our pKa in this situation. So if you have your Ka value, you can just take the negative log. Still here, our weak acid, again, before we get to our equivalence point, our weak acid is greater than our strong base. Again, we'll have to do stoichiometry to figure out how much of our weak acid has been consumed. And then after that, we'll solve using, again, a weak acid, our Ka right there. All right. If we are at our equivalence point, our strong base should be equal to our weak acid, but there will be a basic salt present at equilibrium. So we'll have to use the Kb value of that basic salt in order to solve our pH there. So that will be like a after you've done your stoichiometry to figure out, or after you figure out how much of your basic salt you have, then you'll find the pH of a salt essentially. And then right here, anytime we're past the equivalence point, we have more base than acid. So we'll just use stoichiometry to figure out how much base we have. And then we'll just do POH of our strong base. So at different points on our equilibrium chart, we have different calculations because we have different things that are in the majority or the minority. So, if I have more weak acid, then I'm going to use my Ka value. But if I have strong base dissociates completely. So it's a much simpler pH calculation there. All right. So we are going to jump in. We're going to do three essentially problems in weak acid and strong base. I'm going to do three. One that is before the titration, like before the equivalence point, one at the equivalence point, and then one after the equivalence point with you guys. And then we'll talk about strong acids and weak bases. I am going to have you guys, I'm going to solve one of them, and then I'll have you guys solve the other two. So that's the game plan. Let's get started. All right. So first off, it says 30 milliliters of 0.1 molar NaOH is added to 50 milliliters of 0.1 HF. And then we have the Ka of HF is 7.2 times 10 to the negative fourth. Determine the pH of the final solution. I did give you guys plenty of room to work, but I'm going to come up here. It's really the first thing we need when we're solving titration problems is we need our net ionic equation. Now, for these, it's a little bit different. Our net ionic equations are going to look a little different since our weak acid doesn't completely dissociate the way a strong acid would completely dissociate. So I'm going to have NaOH plus HF. And again, those are going to, it's a double replacement. So outsides with outsides, insides with insides. I'm going to end up with H2O plus NaF. All right. That is a neutralization reaction. All right. Everything is going to break up except for the HF and the H2O. So really the only things that are going to cancel out then is the sodium, and I'll be left with OH plus HF yields H2O plus F minus as my net ionic equation here. Again, because HF doesn't break up, so the fluorine won't cancel out. Even though sodium fluoride would break up. HF doesn't completely dissociate because it's a weak acid. Okay, then we're going to solve them very similarly to how we solved them before. And we're going to start by just figuring out how many moles of hydroxide and how many moles of HF we have here. So we'll start by doing that. So I have 30 milliliters of 0.1 molar sodium hydroxide. So for my hydroxide, to figure out how many moles, I'm just going to calculate or multiply my molarity times liters. So my molarity is 0.1. Try 0.1 times my liters, which again, it's in milliliters, so we have to divide by 1,000. So we'll get 0.0300 liters. Multiply those together, and we should have 0.0300 moles of hydroxide that we're working with. Then again, we don't need to figure out how much HF it's reacting with, how many moles of HF it's reacting with. Now again, HF doesn't break apart, so we are going to solve for the moles of HF, not the moles of OH. So again, it's molarity times liters. So my molarity of my HF is 0.1 times the liters, it's 50, so 0.5. Solve that, and I end up with 0.0050 moles of HF. Okay. We are not at our equivalent point. We don't have equal moles of hydroxide and hydrofluoric acid, so we are going to have to do a BCA table. So BCA table, remember, it's just very similar to a rice table where we take our reaction. So I have OH negative plus HF yields H2O plus F minus. So our before, when we start our reaction, I have 0.003 moles of OH. I have 0.05 moles of HF. Doesn't matter how much water I have, and I shouldn't have any fluorine ions. Now then my change, because these are reacting in a 1-to-1 ratio, so I'm going to subtract by the smaller one because the smaller one is going to be what's completely consumed. It's basically a limiting reactant problem. So in this case, I have less OH, so I'm going to subtract by the amount of OH that I have here. And it's going to be added over here on the fluorine side. All right, so after, we'll have no hydroxide. I will have 0.002 moles of hydrofluoric acid and 0.03 moles of fluorine. All right, this is going to be a weak acid, and this is a conjugate base. So, and it's also going to be one of our common ions that our hydrofluoric acid does break up into. So this is going to be significant, and we are going to have to use that as well. So now what we need to do is we need to figure out what concentration we have of hydrofluoric acid as well as fluorine ions in order to do our rice table to figure out our pH of our hydrofluoric acid. So our concentration of our hydrofluoric acid is going to be equal to the number of moles, which is 0.02 over our volume. So in this case, our volume is going to be 30 milliliters plus 50 milliliters, which gives us 80 milliliters or 0.8 liters. So divide those out. And for my HF, I got 0.0250 molar hydrofluoric acid. And for my fluorine, we got to do the same thing because again, fluorine is one of the things that breaks apart into. So this is kind of taking some common ion there from our equilibrium unit as well. Just that if we have a common ion, the amount that our hydrofluoric acid is going to be able to break up is going to be less because we have that common ion there. All right. So I have 0.003 moles of fluorine. I feel like the zeros just make this so confusing. It'll be in the same volume, again, because we added together 30 milliliters plus 50 milliliters. And then we'll solve that one. So plug it into your calculator. And I got 0.0375 molar fluorine. Okay. So now that I know the concentration of my hydrofluoric acid and the concentration of my fluorine, I can do a weak acid pH calculation. So this will just be like a normal weak acid pH calculation that we've done before with the Ka value, and we'll just solve it. So first off, we need to talk about what hydrofluoric acid is going to break apart into. So hydrofluoric acid is going to break apart into hydrogen plus fluorine. All right, we're going to do a ice table or a rice table. So our initial for our hydrofluoric acid is just coming from over here. According to that, I have 0.025 molar hydrofluoric acid. I have no hydrogen, but again, I have that common ion of our fluorine, of our conjugate base there, of our fluorine. So got to take that into consideration. So that will be 0.0375 molar fluorine. All right, now our change. So some of our hydrofluoric acid is going to break apart, and it's going to break apart into hydrogen and fluorine. So at equilibrium, we will have these equations. And we will plug those into our Ka expression. So our Ka is equal to concentration of hydrogen times our concentration of fluorine all over our concentration of hydrofluoric acid. And we can go ahead and plug in the values that we have. So our Ka from our problem is right there, 7.2 times 10 to the negative fourth. So 7.2 times 10 to the negative fourth. It's going to be equal to X times 0.0375 plus X all over 0.025 minus X. This is a pretty small Ka value, so we can, again, going back to a little bit of equilibrium, we can say that these X's that we are subtracting and adding are going to be really negligible and really not going to affect those values very much. So really we can say that X times 0.0375 divided by 0.025, because they're pretty small. It's a pretty small Ka value. So really that's not going to super affect it. All right. And then once we've done that, we can go ahead and solve for X. So you guys go ahead and take a minute, solve for X. And when I solved for X, I got 4.8 times 10 to the negative fourth. So from our equation, X is equal to our hydrogen ion concentration. So our hydrogen ion concentration is equal to 4.8 times 10 to the negative fourth molar hydrogen. So the question asked for my pH. So my pH would be equal to the negative log of my hydrogen ion concentration, which is 4.8 times 10 to the negative fourth. So my pH would be, when I plug that into my calculator, I get 3.32. These problems are like a marathon. There's a lot of steps. Some of them are easier than others, but yes, there are a lot of steps involved in these problems for sure. Okay, so let's go ahead and try the next one. All right, so we're using the same equation again, just with our sodium hydroxide being added to our hydrofluoric acid, but this time we have different values of sodium of the hydroxide and HF being added. So I have 50 milliliters of 0.1 molar NaOH. So I need to find the concentration of my hydroxide, which is going to be equal to my molarity times my liters, which gives me 0.00500 moles of hydroxide. Also need to figure out the concentration of my HF. So my HF is going to be equal to 0.05 liters times my molarity, which gives me 0.00500 moles of HF. All right, we can already see that those are the same. So we can tell that this is at the equivalence point, which means that we're going to have a basic salt at our equivalence point, and we'll have to calculate the pH of that. So moving in from there, I'm going to go ahead and do my BCA table. So OH plus HF yields H2O plus F minus. All right, my before, I'm starting with 0.005 moles of HOH, starting with 0.05 moles of HF. Water doesn't matter, and I should have no fluorine. Guys, these are the same, so we're going to subtract both of them, the same amount. And after, we end up with no hydroxide, no hydrofluoric acid, but we do end up with 0.0500 moles, moles of fluorine. Now, this is our conjugate base. It's also going to be a weakly basic salt. So what we are going to do now is we are going to find the pH of that basic salt. All right, so we're going to find the pH of that basic salt. So first thing we need to do is calculate our concentration of our fluorine. So our fluorine is going to be our concentration is moles over liters. So I have 0.005 moles of fluorine divided by my total volume, which in this case, my total volume is going to be 0.1. So, because I have 50 milliliters plus 50 milliliters gives me 100. So my total volume will be 0.1 liters. So when I solve, I get that I have 0.050 molar fluorine. Okay, so we're going to come over here, and I'm going to zoom in a little bit since I'm a little bit running out of space, and do our rice table for our basic salt. So our basic salt, our fluorine, is going to react with water. And when it reacts with water, it is going to, because that's it's basically going to steal a hydrogen from the water, forming hydrofluoric acid plus hydroxide. All right, so let's go ahead and do our table. So our initial for fluorine is the concentration that we just solved for, which is 0.05. Water doesn't matter. We should have no hydrofluoric acid and no hydroxide. So our change, we're going to subtract by some amount of our fluorine and plus on our hydrofluoric acid and our hydroxide. So our equilibrium will be 0.05 minus X. HF will be X and hydroxide will be X. Now, guys, we are using this is a weakly basic salt. So we don't need the Ka value, we need the Kb. However, we can figure that out. Based on using the Ka of the weak acid, we can figure out the Kb of our basic salt here. So if you guys remember, Ka times Kb is equal to our Kw, our water constant. So we can plug those the numbers that we have in. So we have our Ka, so Kb is going to be equal to our Kw over Ka, and we can plug it in. So Kb is equal to 1 times 10 to the negative 14th divided by our Ka value, which from our problem is 7.2 times 10 to the 14th. I'm sorry, times 10 to the negative 4. And when we solve, we get that our Kb value should be 1.4 times 10 to the negative 11th. All right. And then we'll plug that in as our equilibrium expression to figure out our X so that we can solve for our hydroxide ion concentration here. So our Kb is going to be equal to the concentration of HF times the concentration of hydroxide all over the concentration of fluorine. All right, and we can plug it in. And once again, this X is we have a really small Kb value, so it's not going to dissociate that much. So that X is pretty much going to be negligible. So we can just ignore it when plugging it in. So I'll have X squared, since both hydrofluoric acid and hydroxide are X over 0.050. Plug it on in and solve for X. So when I plug it in and solve for X, I get that X is equal to 8.4 times 10 to the negative 7th molar. So that means my hydroxide ion concentration is equal to 8.4 times 10 to the negative 7th molar. All right. And then we can plug it in to solve for our POH. So our POH is equal to the negative log of our hydroxide ion concentration. And when I plug that into my calculator, I get that my hydroxide ion concentration is 6.08. A problem asked for pH, not POH. So pH is equal to 14 minus our POH, which is 6.08, which gives me a pH of 7.92. So that would be my pH of that problem, 7.92. So we can see that it is a basic solution because it has that weak base there, even though we're at the equivalence point here, where our hydrogen and our hydroxide concentrations should be equal, but because we have that basic salt present, our pH is going to be basic. Okay, we're going to solve one more of these weak acid, strong base problems, and then we'll talk about weak base and strong acids. Like I said, these problems are kind of a marathon. They've got a lot going on, but I don't think they're that bad once you kind of figure out what you're actually solving for at the end. I think they're not too bad, hopefully. So let's do our last one. So we have 60 milliliters of 0.1 molar NaOH is added to 50 milliliters of 0.1 molar HF. Ka of HF is 7.2 times 10 to the negative 4. We need to determine the pH of the final solution. Okay, so once again, we are going to calculate our hydroxide ion concentration and our hydrogen ion concentration, or our HF concentration, or I'm sorry, our moles of hydroxide and our moles of HF. So my hydroxide ion concentration is equal to our liters, which is 0.6 times our molarity. And when we solve, I got 0.0060 moles of hydroxide. And then our HF concentration is going to be equal to our liters, which is 0.5 times our molarity, which is 0.1. And when we solve there, we get 0.005 moles of HF. So let's do our BCA table. So I have, again, we're using the exact same equation we've used pretty much this whole time. So hydroxide plus hydrofluoric acid yields H2O plus fluorine ions. So before our reaction, I have 0.006 moles of OH. I have 0.005 moles of HF. Water doesn't matter. And I have no fluorine ions. So our change is going to be, we're going to subtract by a smaller number here. So we have less moles of HF, so minus 0.5 or 0.005, and add by 0.005. So after, I will have 0.01 moles of OH, no HF, and 0.05 moles of fluorine ion. So here we have a strong base and a weakly basic salt. So we can actually ignore our fluorine and we're just going to use our hydroxide ion concentration to calculate our pH because, again, we have a strong base and a weak base. We can ignore the weak base. All right. So for our hydroxide ion concentration, first thing we need to figure out is what is the concentration? So moles divided by liters. So in this case, I have 0.001 moles of hydroxide divided by our liters, which should be 0.110 liters. We solve, that gives us the concentration of 9.90 times 10 to the negative third molar OH hydroxide concentration. Since this is a strong base, we can just then plug it into our normal equation. So since it's a strong base, I can just come on over here, say that my POH is going to be equal to the negative log of my hydroxide ion concentration, which is 9.0 times 10 to the negative 3 molar. So I get that my POH is 2.04. Can then use my POH to solve for my pH, just subtract 14 minus 2.04. And I get that my pH is equal to 11.96. And that would be my answer. And again, just because we have that strong base there, we can just do a normal pH calculation, which makes it so much easier to solve this problem. All right, guys, we're going to do one more problem, and then I'm going to leave the rest for y'all to do on your own. So we're going to talk about now weak bases and strong acid. So before the equivalence point, a weak base equilibria exists. We have to calculate this stoichiometry and then the weak base equilibria. At the equivalence point, an acidic salt is present, so the pH is going to be below 7. And after the equivalence point, strong acid is the dominant species, so we can just use our hydrogen ion concentration to find the pH. We are once again I'm going to zoom in to the graph a little bit on a different sheet so I can point out some different parts of this graph for us. So this one, again, we have the titration for 100 milliliters of 0.5 or 0.05 molar NH3 with 0.1 molar HCl. So at the beginning of before we've done anything with our reaction, we have weak base only. So we would just use our Kb value and do a normal weak base calculation. As we move along our graph, right here, we would have more weak base than strong acid still. So we'd have to figure out how much weak base we've consumed, then use our Kb to solve for that. Just like last time, our strong acid right here, when we're halfway to the equivalence point, our pOH is going to be equal to our Kb. Kb is almost the exact same as Ka. So to solve for Kb, you would take the negative log of your, to solve for pKb, you would take the negative log of your Kb. The lower your Kb value, the stronger your base. It's just another way to measure strength of acids and bases. So pOH is equal to Kb when we're halfway to the equivalence point. Again, before we get to our equivalence point, we would still have more weak base than strong acid. So we'd have to figure out how much we consumed and then use our Kb to get to figure out the weak base pH. At our equivalence point, our weak base is equal to our strong acid, but there is an acidic salt present. So we would have to do the pH calculations for our acidic salt. And then anytime we're above our equivalence point, we have more strong acid. So we just need to figure out how much strong acid we have and then just use the concentration of our strong acid in order to find the pH. So pretty much the same process that we were doing last time, but this time instead of having a weak base, we'll have a weak acid as our calculation that we're doing. All right, so with that, let's hop in to solving these problems. All right, and like I said, I'm going to solve the first one with you guys, and then I'm going to leave you guys to do the next two on your own. All right, so it says, calculate the pH when 100 milliliters of 0.050 molar NH3 is titrated with 10 milliliters of 0.1 molar HCl. And we have the Kb of NH3 is equal to 1.8 times 10 to the negative 5. Okay, so first thing we need our, oh my word, totally lost my train of thought, our net ionic reaction. So in this case, we have NH3 plus HCl is going to be equal to, and this one we have a Bronsted-Lowry reaction going on here. So our acid is going to donate a hydrogen to our base. So NH4 plus Cl minus. Our HCl completely dissociates. Our NH3 does not dissociate. So the only thing that cancels out on both sides is our Cl. So we end up with NH3 plus H plus yields NH4 plus. And that will be our net ionic equation here. All right, so first thing we need to do is figure out the concentration of our NH3, our ammonia, as well as our hydrogen. The moles of our NH3, the moles of our hydrogen. So to solve for that, we start with our NH3. And it's going to be our liters times our molarity which gives me 0.005 moles of NH3. Let me rewrite that because that's kind of ugly. And then for our hydrogen ions, same thing. So I have then 0.010 liters of hydrogen times 0.1 molar gives me that I have 0.001 moles of H plus. So let's do our BCA table and figure out, we can see that we are going to consume all of our hydrogen ions since we have less hydrogen ions, but let's figure out how much of our weak base we have as well as our basic salt as well. So we have our net ionic equation, NH3 plus H plus yields NH4 plus. So we're starting with 0.005 moles of NH3. We're starting with 0.001 moles of H plus and no NH4. So that would be our before. Our change is that we're going to, we have less moles of hydrogen. So that's how many can react because again, it's like a little limiting reactant problem. And so after we would have 0.004 moles of NH3, no hydrogen, and 0.001 moles of NH4. Now then, again, so we have our weak base here, so we're going to use that in order to solve for our, calculations, but NH4 will be a common ion there, so we do need to use that as well. So we need to figure out the concentration. It's also our conjugate acid, so we need to use our weak base plus our conjugate acid to figure out our pH of this solution. So I'm going to figure out first the concentration of NH3. So moles divided by liters. In this case, I have 0.04 moles of NH3 divided by our volume, which is 0.110 liters. Because we added 100 plus 10 milliliters essentially. So that's where we got that from. And I get that my concentration of my NH3 should be 3.64 times 10 to the negative 2 molar NH3. Also need to figure out the concentration of my NH4 plus. So I have 0.001 moles of that divided by 0.110 liters gives me 9.09 times 10 to the negative third molar NH4 plus. Okay, now we're going to do our rice table in order to figure out our KB and all of that stuff. So our rice table, our reaction that we have when we have NH3 is that NH3 reacts with water to produce NH4 plus OH minus. So since it reacts to form that OH minus, that's where we get that this is a base because it reacts with water to form that. So we have 0.0364 as our starting concentration of that. I just converted it out of scientific notation. Water doesn't matter since it's a liquid. And then we have 0.00900 of our concentration of our NH4, and we shouldn't start with any hydroxide here. So then our change, we're going to lose some amount of NH3, and it's going to add to our NH4 plus our OH. So our equilibrium is going to be 0.0364 minus X, 0.00900 plus X, 909. And then our OH will be X. again, guys, our KB value from our problem is 1.8 times 10 to the negative fifth. So these x's here can be considered negligible when we plug them in to our equilibrium expression. So our equilibrium expression is going to be NH4 plus times the concentration of OH minus all over the concentration of NH3. And again, like I said, those x's can be considered negligible. So when we plug it in, we can just put that our Kb of 1.8 times 10 to the negative 5 is equal to 0.00909 times x all over 0.0364. And then we can solve for our x. So x would then equal 7.21 times 10 to the negative fifth, which would also be our hydroxide ion concentration. Since in our equilibrium expression, our hydroxide ion concentration was just x. So we can plug that in to solve for our POH. So POH is equal to the negative log of that, 7.21 times 10 to the negative fifth, which gives us that our POH is 4.14, and then subtract that from 14 to get our pH. So we get that our pH is 9.86. Boom. That is strong acid, weak base titrations. So it's very similar to weak acid weak acid, strong base. So it's very similar. So I want you guys to try to solve the next two on your own and then check back on the answer key to see if you got it. And then feel free to email myself or Mr. Oglesby if you guys have any questions about titrations. All right. Have a great day. Bye, guys.